Hello, I'm Jeff Disher. Welcome to another video. Today we're going to be talking about sort of a follow-on from what we did last time with Boolean Logic. Today we're going to be talking about combinational logic. So combinational logic refers to how we go from the very simple kind of Boolean logic expressions we were working with into much more complex things which will later become what we use to actually talk about how CPU instruction execution actually works. Because really, this is kind of how you get there. So at its core, the actual problem of combinational logic is trying to figure out, given a set of inputs that I can use to come up with a certain output, like make a certain decision, how do I actually put the right logic gates together to actually allow me to see how this would work, to actually kind of build something that I could even put in hardware, or just expressing logically in some sort of logic diagram how the relationship between the ideas actually works. Now we're going to be starting with something which is kind of a contrived example, yes, but it's something that we can actually use to have a very simple idea and something we can actually base some later discussions on later on in the video. So we're going to be talking all about how do I decide whether or not to go outside. So there's a few simple inputs for this. For example, maybe am I bored or not? Maybe I want to go outside if I'm bored. Do I have errands to run? Maybe that's some reason why I'd need to go outside. And what about the weather? What if it's raining? Maybe I don't want to go outside if it's raining. So what we're going to do based on these inputs is actually come up with sort of a bunch of rules where we're describing this is how I would actually make the decision, what I actually would want to do. So we're going to say, all right, if I'm bored and it's not raining, then I think I'll go outside. And if I have errands to run and I'm bored, then I'm going to go outside whether it's raining or not. Given these two basic rules, I can actually come up with a truth chart which will actually describe what we're going to do. So first of all the inputs I've changed just into letters, just to keep things concise. So whether we're bored is going to be variable A, whether I have errands to run is B, and whether it's raining is going to be C. And now I've filled out the rest of the truth chart showing when these things have different values, what is the actual output? Will we go outside or not? And you can see there's only 3 cases where we actually will. But looking at this, it's not obvious how you'd actually connect all of these things. What's the actual pattern here? And for that, we're going to get into something called a Karnaugh Map. Now, a Karnaugh Map, or K-map, is something which it's really these days more of just an exercise in understanding the relationship between different ideas. There's other ways of solving this kind of problem, which you do in software, but this is a good way that actually, it's very visual, it means something to humans, because it actually takes advantage of the human mind's ability to see patterns everywhere, and it actually exploits that to make it easy for a human to just figure out this problem on paper. So first of all, what we're going to do is put the data we've got inside this truth chart into a K-map. Now this K-map here is going to be the structure we want. You see, it's not just a table, it's actually a grid. So we're going to put the A and B on the top, kind of along the top, and the C along the side. It doesn't really matter how you orient these things, but you just kind of want it to be balanced because it's a bit easier to work with that way. And now the important thing to realize as well is the way I've counted these values out does not look like binary. It's not looking like it's counting in binary, at least, because remember, you're not going from 0, 0, 0, 1, 1, 0, the way you go from like 0 to 1 to 2 in binary. No, because a K-map is using something called gray code. Now this is when you actually put binary values in a sequence such that only one digit changes between any 2 adjacent numbers. Well, why would you do this? Well, because we're trying to see a pattern in how the values change. We don't actually care about whether it's binary or just a set of bits. We're not trying to think about it as a number at this point. All it is a set of inputs. So we're just trying to arrange it in such a way that we can see the pattern when one value changes from one column or row to the next. So now that we've got the K-map laid out, we'll populate it with the data that we got from the truth chart. And now we can see, okay, fine, there's the 3 values there as they were before. Well, now what? Well, the thing you're trying to do with a K-map is you need to identify all the groupings of 1s. You can do this with 0s as well, but in this case it makes more sense to do it from 1s. That actually make up a rectangular area which is a power of 2. Well, why a power of 2? Because a power of 2 means that you're actually grouping different variables that you're passing in as inputs together. So in this case, there's actually not very many options. You can see that we basically just have 2 ways of doing it. We can connect these 2 here and these 2 here. And that's about it. And the thing is, so how do you determine, well, which one do I use, which one stands alone? And the answer is it doesn't matter. In fact, it's easier just to allow them to overlap. So what we're going to have here is 2 different expressions. So, okay, now that we've got these rectangles highlighted, what do? Well, we figure out what they describe. So the first one here is actually going to be A and not C. So it's as long as one of those is true, as long as A is true and C is false, it doesn't matter what B is. So that's going to be one of the values we're going to get. So we're going to write it down at the bottom as A times C bar, which means C negated. Now the other rectangle here actually describes a different kind of axis. So in that case, it's true whenever A is true and B is true, but it doesn't care about C. So in that case, we're going to say, okay, that's A and B. And now we're going to be combining these, saying, well, we're really only interested in, we know that it's true if either of these cases is satisfied. So it's an OR relationship. So this is how we'd write it together. So now that we've got this basic relationship that describes, here's this sort of the A C bar plus AB, well, we know from there we can change this into a sequence of logic gates and put them together like this. Now note as well, it could be actually interesting, I'm not going to worry about it too much in this case, but you could also simplify this or refactor it differently so it was actually A and C bar or B, and that would give you a system like this. They're both equivalent, it's just going to be different layouts of how things are connected. So now that we've got this combinational logic, this answer, this simple connection of logic gates that actually will answer the question of whether or not to go outside, we can use this as an example for other discussions. So first of all, after I put in my inputs, how do I know when the output's done? Because remember, these things aren't instantaneous. The gates are actually some physical number of transistors, and transistors take a certain amount of time for their for their values to switch based on their inputs. So we have to put inputs into this and then just kind of wait and at some point in the future read the output. But how do we know when that happened? And if we're trying to build a more complex system where something else now depends on this, or we're trying to store this somewhere maybe, how do we synchronize everyone? There's all these different components and nothing actually forces them to be in any sort of synchronized state. So this is what brings us to something called a clock. Now you might notice this is starting to get closer to the ideas that actually do exist in CPUs, because this is the problem that your CPU clock solves there. It actually gives you that point where you know that an intermediate operation is completed. So that's why a CPU with a higher clock speed generally refers to something that's faster, as long as it's got kind of the same design. So in this case, how do you use the clock? Well, the clock is just going to be a pulse that comes in from some sort of quartz crystal or something like that that kind of can produce very, very high frequency, short pulses. Because after all, in a modern CPU, you're going to be getting a few billion of these pulses per second if you're running at like 2 gigahertz or something like that. So in this case, effectively what we're doing is we're going to take the output of this thing and the clock input, and we're going to we're just going to AND them together. And the result of that will be the answer that you actually have. And you know that that answer will only be returned because of the AND gate when the clock pulse comes in. So you have a single point where you know the answer will be true or false. Now, how do you determine what kind of clock frequency you can use? Well, this is affected by various things about just the implementation hardware itself, which is often why clock speeds would increase when the fabrication technology would get better and CPUs could get smaller, because it would just take physically less time for certain things to happen. But the other thing that you often look at is this concept of gate delay. It's the idea that a gate itself actually represents essentially a timeable unit of thinking. So from that we can say, okay, in this case we've got 2 gates to get through to get the answer. So this would be a 2-gate delay solution. Now other ways of solving this problem, or other kinds of problems you need to solve, if they have longer gates, if they have more gates involved in them, a longer furthest path through the whole system to get to that gate, to actually get to the final gate, they'd have a longer gate delay. And so that's what on a CPU would determine what your maximum clock speed can be, is the longest sequence of gates in any one intermediate operation. Now, okay, that's fine for that simple example that we had, and we know now how to put things together. But how else could we start putting together more pieces of logic? What happens if we're trying to do more than one, we're trying to think about more than one thing or something like that? Well, that's where we start getting whole sequences of values that are either stored or just kind of represent an in-flight state of some computation. And when we put these things together to think of them as one unit, we call them a register. Now this is of course a term that you'd be familiar with. from just the way the terminology used to describe registers in CPUs, and that is where we're going. So it might become a little bit clearer now where the next video is going to go and how this gets from the Boolean logic up into that point. Okay, so given that we've got a register here, we're not going to worry too much about really how the values inside it are stored. We're just going to assume that, okay, however they're stored, they represent essentially a set of outputs. But similarly, they also can represent a set of inputs, because with a register you might need to update it, for example. Now whether that's the same physical piece of hardware or whether it's just a logical idea that these are the same over time, it doesn't really matter. That's kind of an implementation detail. So let's talk about what's probably the simplest kind of operation you could perform on a register itself. Something that is very, very trivial to implement, very, very fast, and in fact it exists in modern CPUs because of that reason, and it's used in a lot of kinds of optimization because it makes things very fast. So it's an instruction that you will always see a lot of. And this is going to be a shift instruction or a rotate instruction. Now a shift instruction literally just means take all the bits and shift them over one, or more than one. Now a rotate means shift it over, except any bits that fall off the end, put them back around to the beginning. So that way it actually rotates the value instead of just shifting it off into oblivion. So okay, how you'd actually do a shift is fairly simple. You just kind of wire everything from one side over by one bit to the next. But then say, okay, well, maybe I want it to sometimes rotate and sometimes shift. So then you've got to also wire in this end piece up to the beginning, but you have to AND it with something else. So what if we said, what if we need a way to parameterize this kind of operation now? What we need is an instruction. So what if there was another register somewhere that had the current instruction we're running? It's binary that describes that. It's just a bunch of signals, don't worry too much about it. And it's just all the instruction is are you rotating or not? So then we can flow that into this decision in the AND gate. So now if that bit that says we're rotating is set to true, we'll rotate. If it's set to false, we'll shift. And so this is where you can start seeing the idea of this is how instructions are actually built. They're based around, we've got some combinational logic inside the CPU that can actually perform certain operations. But how do we parameterize them? How do we even choose which operation to perform? And that's where you run into things like this. The instruction itself will actually have bits that tell you what registers do I use? What instruction am I using? What other options within the instruction am I going to actually be applying in this case? And so that's what we'll be getting into next time. So anyway, I hope that was interesting and informative and kind of makes sense as the step from the Boolean logic that we did last time into the CPU instruction execution we're going to be doing next time. So let me know what you thought of the video and if you have any questions, and I'll talk to you later. Thanks. Bye.